Today's lesson will be focusing on section 3.4, concavity and the second derivative test. To define concavity, let the function f be differentiable on the open interval I. The graph is concave upward or downward given the right parameters. When f prime is increasing on the interval of I, then it is concave upward. If f prime is decreasing on the interval I, it is concave downward. Visually, this is represented as upward and downward concavity. Points in a graph are also able to be concave at different moments between intervals, such that you can declare that this is concave downward and this is concave upward in the interval, say, negative infinity to 0 and 0 to positive infinity. In order to test for concavity in a function, whether if it's up or down, without using a graph, we have to determine the x values on the open interval I for the second derivative of the function. For all values f of x of the second derivative that are greater than 0 in the interval, the graph would be concave upward. And for all those that are less than 0, it would be concave downward. We're given an example problem in the slides. F of x is equal to 6 x squared plus 3. First steps that we have to do, we have to find the first derivative. We can bring this down to 6 x squared plus 3 or negative 1. To simplify this in a more linear form, then to find the derivative, it would be negative 6 x squared plus 3 to the negative 7 times 2x after going through and using the chain rule. Taking it the next step further, we'll have negative 6 times 2 times 2x. As the final answer will come out to 36 x squared minus 1 power of x squared plus 3 cubed. Now we will determine when f double prime of x is equal to 0 and the intervals of when x is equal to plus or minus 1, with the function of the second derivative of x when it is equal to 0, we will find that the critical numbers are when x is plus or minus 1. This will determine that on the intervals negative infinity to negative 1, negative 1 to 1, and 1 to negative infinity are all the intervals that we could check for concavity. In these intervals, we can use any value between the two values to determine and test for our conclusion whether or not they're concave upward or downward. So we'll be using negative 2, 0, and 2. So this test will determine that f prime -2 is going to be greater than 0 on the final value. F double prime of 0 is going to be less than 0 on the final value. And f prime of +2 is going to be greater than 0 on the final value. So this will prove that this is concave upward, downward, and upward. If we were to show the graph, this would prove the same. This is more or less how the graph would look, seeing that we're going to get a concave down, up, and up on these intervals. These points right here are also known as points of inflection. They're determined as when the graph of the function has a tangent line at the point C and f of C, then this point of inflection of the graph of f, when concavity of f changes from upward to downward or downward to upward. This is determined when we find that the second derivative of the function of c is equal to 0, or if the function of f of c does not exist. These are the two tests to determine whether or not there will be a point of inflection without using a graph. Another example presented in the slides will provide us with a simpler function. F of x is equal to x to the power of 4 times x. First derivative we will find is 4x cubed minus 12x squared. Second derivative is equal to 12x squared minus 24x, which we can simplify into 12x x minus 2. To find the points of inflection, we need to set this equal to 0. We will be able to find that when x is equal to 0 and x is equal to +2, the function f prime of x will be equal to 0. So these will be our inflection points on this graph. We will then present the theorem showing the 0, plugging it into here, presenting us with another 0. So this will be the c and f of c, as well as 2 plugged in to here. So that's f of 2 equal to 2 cubed times 4, which will present us with -16. This is the final determination, stating that we are yielding points of inflection, because we are able to find the c and f of c. And as we presented before, we can test the concavity between the intervals. So given -∞ and 0, 0 and 2, and 2 and infinity. Again, we can pull values, -1, +1, and anything above 2, so we'll do 3. And we can plug those into the second derivative. So f double prime -1 will present us with a value less than 0, declaring that, or a value greater than 0, declaring that the concave is upward. F double prime of +1 gives us a value that is less than 0, concaving downward, and F double prime 3 gives us a value greater than 0, concaving upward. Another test that we can use, the second derivative for, is to determine the relative minimum of a function on a graph. So say that we have this graph presented here with a relative minimum right here, localized as C. This is the full function. If the second derivative of the function with C is equal to 0, if the first derivative, and the second derivative, the function of C, is greater than 0, then the function f of C, right here, is the relative minimum of the whole graph within the given interval. We can determine the relative maximum by seeing the second derivative and seeing that it is less than 0. This will determine the relative max. This determines relative min, but they still have to have the first derivative of C equals to 0. This is shown this would be the relative maximum of the given interval. So the first derivative must have f of C. The first derivative must be equal to 0 for this test to succeed. If the second derivative of C is equal to 0, the test fails, and you'll have to use the first derivative test to determine the relative min or max. It may have one, it may not, but that's why we have multiple different tests. The first derivative tests will have to be used in that situation if the second derivative and the first derivative are both equal to 0. There's one more problem presented to us in the slides, in which we can see this practically. Using the function f of x is equal to -3x to the power of 5 plus 5x3. Finding the first derivative, we get -15x4 plus 15x2, which we can simplify into 15x squared and 1 minus x squared. We can see that the critical points on this are positive and -1, as well as 0. Then we'll find the second derivative, in which -60x cubed plus 30x, which can be simplified again to 30x. It's 1 minus 2x, x squared. Now we simply need to Well, you're going to find the points of C and f of C once again. That will give us -1 and -2, 0, 0, and 1 squared. Remember, we're plugging the x value into the original function to find this, and this is the critical points that we found out of the first derivative. By plugging in the x value found here into the second derivative, we'll find that -1 will result in something greater than 0, prime of 0 will equal 0, and f prime of 1 will present us with something less than 0, giving us a relative max here, relative min, and a test failing here. We'll have to use the first derivative test to determine the cause on why this fails. The slides will discuss and present that after using the first derivative test, it appears that f increases from left to right on x equals 0, and that's why the test fails. You can see this visually. Through the graph provided, 0, 0, 1, 2, and -1 and 2. And the graph is shown to be increasing from left to right. And this will present us with our max, our min, and something that is neither max nor min. I hope everything was informative. Thank you for this lesson.